So we have 2 minutes before lecture, and I would like to raise some questions for discussion. So you are thinking about your future. So what is the right way to have master degree or not to have master degree? To have only master degree and not to have PhD or to have PhD. This is very important. So in 2 words, what I would like to do now in 2 words, but later, thank you very much. Later, I will return to this discussion. So if you are going to academia, then PhD, because it will be more and more and more complicated to be even lecturer, not professor, without PhD. If you are going to industry, it's very big question, because there are companies which likes to have PhD, for example, Google, but there are many situations when it's better to begin earlier, to grow without any PhD, and we will have absolutely amazing results. So please begin to think about this issue, and we will be able to return to it during next days. And this is really important. Okay, now, Samir, please. So, Dr. Samir Abdullah will continue teach this course. And I believe today you will have a bit less theory, but a bit more about implementation.
Yes.
Because implementation here is very important, since data is, I don't want to say large, I don't want to say huge, but I have no appropriate words.
Okay. Thank you so much. Yeah, good morning, everyone. My name is Samih Abdullah. I'm working as a research scientist at the Extreme Computing Research Center here at KAUST. Actually, yesterday you had this talk from Mark Johnson. Can you remember anything about the presentation, the contents? And Jan also joined Mark. Then after that, you had a talk from David Keyes. So David Keyes actually maybe give you some overview about HPC and what we are doing here at the center. I will go from the beginning, but just maybe there is some overlap with what I will say today and what David said yesterday. So I am a little bit young, okay, so I like the presentation or the short course to be somehow interactive between each other. So if you have a question, if you have something, anything you are thinking about when I give you the contents, please let me know. Okay, so stop me and just ask me the questions, okay? So yesterday, Mark and also Jan gave you an introduction about spatial statistics and what's the meaning of that we need to model or to predict spatial. This is the simplest case that Mark discussed yesterday, is to give some modeling and prediction for any spatial region. If we have, for example, some measurement of the temperature around the kingdom, and we need to understand what's going on the climate and weather, what's going on in the next 10 years in the kingdom. This is one example. Another good example, because I don't like to just put spatial statistics close to the climate weather application, because it's also helping other application like the air pollution, for example. We have this project, actually, we will start it soon with the Ministry of Environmental here at the Kingdom. So what if we have air pollution measurements on the whole Kingdom? And we need to know exactly tomorrow what will happen. In 10 years, what's the city that will have a big problem from the air pollution? How to solve this from now? How to put our policy? So all of these stuff can be somehow changed, or maybe we can give some advice based on the modeling of the data that we have now. Okay, the modeling of the data, in the simplest case, as Jan and Mark said yesterday, is related to spatial data. So I have one time slot today. I need to know the measurements on the whole kingdom, and I can predict or not predict. We are calling it, in this case, kriging. We can know exactly what's the temperature in Jeddah, for example, based on what we have in the whole kingdom. So we don't need to put sensors everywhere, just on some places, and we can use the data to do some kind of kriging. What if we need to do a kind of prediction or forecasting in the future? Can we have the temperature on different time slots and start to talk about this and how to predict the measurement? Yes, we can use spatial statistics for this. The problem that Mark and Jan discussed yesterday is the problem of how to solve or how to do this modeling with very large data. This is the main problem. For decades, all the spatial statistics researcher or statistician tries to use methods, develop methods, but they cannot run it. They can run it just for small data sets. But now with the IoT, with sensors everywhere, with satellite images, you have a lot of data. And their method, they cannot run it on the usual machine. And this is why 7 years or 8 years ago, Mark and David Keyes start to do a kind of collaboration to do something large-scale modeling, so to be able to model something on the large scale. To the best of our knowledge, even we know about this, that this is what I will discuss today, the first software worldwide that can handle this large data set. So there is no exist software that can go to 1 million of observation. And I will show you now that developing and designing such a software is not an easy task. You need expertise from different fields. You need also expertise in HPC and data science and spatial statistics so that you can be able to develop such a software. So first, high-performance computing. I think you had David's talk yesterday, so someone will give me a brief definition about what's HPC. I don't want a clear definition, just what you got from David yesterday. Yeah, please.
When you write software on the large hardware that we have or the supercomputing we have to do some specific tasks.
Okay, so developing a software on large-scale hardware to achieve a specific task, right? Okay, others?
So computers that are able to process huge amounts of data at one time.
Okay, computer, so he's talking about the hardware. You said software, he's talking about the hardware, a very large computer that can be able to run maybe large-scale simulations. Okay, others?
And also with high performance, so with lowest energy consumption.
Yeah, David did a good job yesterday. If you reach to this point of power consumption, yeah, David did a good job yesterday. Yeah, so this is one thing also, is to save power consumption. Okay. What else? Okay.
Things need to be coded in a certain way so that they work with the architecture and run parallel with all these different cores.
So parallel processing, this is what you mean? Okay, this is good. Others? Okay, so HPC, all what you said here is correct, but HPC itself, it's a term, meaning that you can run faster. That's it. So there is no hardware, there is no software, there is no power consumption. When you define the HPC, yes, all of these are contents to help to reach to HPC. But HPC, when I am telling you that I need something that runs very fast, that's HPC. I don't care about the hardware. I don't care about if you are developing some software, complicated software. Just I can run this small example in 10 seconds, and you are able to run it in 9 seconds. What you develop is high-performance computing compared to the first code. If you run it on a specific hardware, it's okay. If you have your own algorithm that can run faster, it's okay. So this is high-performance computing in general, okay? However, HPC somehow coupled with supercomputers or large scale or GPUs. So once you see a supercomputer, you can couple it with the meaning of HPC. But as I said, this is just a term that I'm running faster. Okay? I forget about this. So this is my background. Actually, I should start with this. So yeah, I finished my bachelor and master in Egypt, 2005 and 2009. Then I have another master degree from the Ohio State University in 2014, PhD. Then I came, as I said, 8 years ago to work on this project in 2016 as a postdoc, and now I'm working as a research scientist also continuing this project and extend it to different things. This is my research interest. During my PhD, I worked in machine learning, data mining, fault tolerance for large-scale application. Now I am working on statistical computing and HPC. So my major is HPC, and I used it in different ways. So as I said, high-performance computing is a term, meaning that you can run something faster. But you can see some other definition, like the definition I put here is about aggregation of computing power to deliver much higher performance, trying to collect some hardware to get higher performance. This is also, we can call it HPC. But the main point here, why we need the HPC? We have laptops and everything is running fast, and this is what we want. Why we need HPC? Actually, until now, maybe HPC is used on a specific area and specific domains based on the needs. So it's not accessible to anyone to use HPC. So we are using actually HPC for different things. First, handling large-scale computations. If you have some kind of problems, like what Mark and Jan discussed yesterday and will continue today, and it's need to do large-scale computing because of the memory problem, because of the computing problem, because of the power issue, so in this case, you need HPC. Speeding up research and development. Actually, I can say that 70 or 80% of the usage of supercomputers today is related to research. Okay, most of the scientific computing need large-scale computing, need supercomputers, and this is why 70 or 80% of supercomputer is just for research. And you can see this. We'll talk about supercomputers now, but most of the countries developed supercomputers just to develop the research. But you cannot just recently. But before that, so 1 or 2 years ago, but before that, companies do not care to develop their own supercomputer or run something. But now we can see Microsoft, we can see Amazon and other companies starts to develop their own supercomputers to run some computation that they cannot. But for a long time, supercomputer is just for research. Advanced simulation capabilities. Again, for a long time in research, that they are developing or doing simulation in small scale. And they need now to go large. They need to know what's going on in the future. Of course, research is something that one step up the industry. So you need to see in the future, if we have more measurements, what will happen. In the future, if we have more data, what will happen. So this is why also research is needed. Big data analytics. So also, if you need to do some kind of data mining, machine learning on the data that you have, you will need supercomputers. AI and machine learning. Now, recently, in the last 2 or 3 years, has become a factor in industry. So big companies like, again, Amazon, Microsoft, even Google, Facebook, they start to have their own supercomputer because they think that this is one step up other companies to work on. Okay, and they have the money to develop such supercomputers, and this is why it starts now to be an industry. Also, it's very important on the national security and defense. Supercomputer is very important to do, again, data analytics, but related to armies and other things that can make you one step up other countries, maybe neighbors or some other problem. So it's also very important, and you can see that most of the supercomputers in the US is on the DOE labs, okay, Department of Energy and Department of Defense, and all of them on the national labs. Very secure, and no one can access them very easily. So it's nothing. It's not something that's the country can ignore. Okay. So when we talk about HPC, we are talking about two main concepts: parallel computing and distributed computing. Parallel computing meaning one machine that you have your laptop. Once you have a multi-core machine that have many cores, you are doing parallel processing. So most of the machines that exist today has multi-core capabilities: 2 cores, 4 cores, 8 cores, up to now we reach to 192 cores. So once you have multi-core in your machine, this is the parallel processing. But again, when we talk about, forget about the power for now, but when we talk about HPC, we are talking about two things here very important: software and the hardware. Your hardware that support parallel processing, and your software that can take advantage of this. So maybe you have a multi-core in your machine, but you are not using it. You are running your software sequentially, okay? So you should have the two parts. So parallel computing meaning the multi-core machine. Distributed computing meaning that we have something like cluster or supercomputers. You have separate nodes, separate CPUs. Those CPUs somehow connected to each other using a very high-speed network. And they are solving the same problem at the same time. Okay, so let's talk about this in the next slide. But for now, we need, when we talk about HPC, to talk about parallel computing and distributed computing. Scientific computing, as I said, for a long time, in software like MATLAB and R, and I think you use some of those software during your study, is used for very small scale. Okay, even you are solving something, you are solving something very small. Some capabilities of parallel computers now exist on some language like MATLAB and R. So you can run multi-core, for example. In MATLAB, you can speed up your computation a little bit by using all the cores in your machine. But again, you will stop at a specific level. So I said at the beginning, when we talk about HPC, we are talking about software and hardware. Now I will say when we are talking about running something faster, we are talking about two things again. Your power, computing power, how many cores you have, what's the speed of each core, for example, how many nodes you have, and the memory you have. This is very important. Because if I need to solve a problem for a big data set, and this data set is about 1 terabyte, and I can solve this using one core in, for example, 10 seconds, a very fast operation, I will have a problem to store this big data set on my memory because the memory on the laptop cannot handle this. So this is a very important factor. So it's not just the speed up that I can achieve by adding more computing power, but also about the memory I have that can handle this problem or not. So as I said, we can do scientific computing now using those software, using parallel computing, but not distributed computing. We need a different way. Also, we can do advanced scientific computing to do very large scale and other things, but at that time, we need to add the distributed version. So first, let's talk about parallel computing. Parallel computing meaning, as I said, we have a task. We can divide it to small tasks. We have a multi-core capabilities on my machine, and I can parallelize my code. So let me go to this slide. Yeah, this slide first, then I will go back. In parallel computing, since it's on one machine, you can see that I have a lot of computing power, maybe CPU, maybe GPUs, but all of them is using the same memory. So on your laptop, you have one memory, but maybe you have multi-core. This is I am calling parallel computing. When I go to distributed computing, we are talking about different computers. Think about supercomputers or distributed system as this. You have different computers. You connect all of them with very high-speed network, and you ask them to solve the same problem. Now the architecture is a little bit different. You have one CPU or more again, have its own memory, and another CPU, its own memory, another CPU, its own memory. So we have different architecture, and this is why the language to talk to each of those architectures are different. So the language here is not the same language here. You are talking about a lot of people can see the same thing, and they are working together to solve or to achieve a goal here. In another side, you are talking about people. They have their own data, their own information, and you ask them to solve the same problem. So the two architectures are different. So this is the parallel computing. A lot of processing unit having the same memory, and they are trying to solve the problem. Actually, this kind of computing started 2007, this kind of architecture, after what people said end of Moore's law. How many of you hear about Moore's law? I think David mentioned this yesterday, or not? So can anyone tell me something about this? Okay, go ahead.
This law, it basically predicts how the technology of semiconductors may be developed. So when transistors will be in a CPU or in a microprocessor. So
Okay.
I think, as I remember, that it predicts that every 2 years the number of the transistors in a microprocessor will double. But now we are reaching a time that it's kind of not possible, or we are facing a lot of problems if we want to keep making these transistors smaller and smaller. So we are reaching like a size that is very near to an atom size.
Yeah, this is very nice. Yes, Moore's law it's from 1978. This guy said that every 2 years, the speed of the processor that we have is doubled by 2x. And the number of transistors are doubled by 2x. And we will keep this forever. Okay, so he predicted this, and actually it works for more than 50 years. No one, even vendors, research, cannot actually destroy this. So this is actually happened, as you can see here. It's very linear, that all the new processors are achieving or trying to confirm what Morse said. However, we have some problems during that. For example, in 2007, we had a problem that when the vendors start to increase the number of transistors on a single CPU, they have a problem because you have one CPU. You need to double the number of transistors, so make the transistor smaller. So we are talking here about some kind of research to reduce the size of the transistor physically. Then how to fit this on one chip. We cannot make a CPU like that, so we still need to obtain a specific size of CPU. In 2007, they have a problem. They cannot reduce the transistor anymore, or they will have two things. First, the transistor will not work correctly. So transistor is what? Transistor is doing what? It's 1 or 0, so it's trying to do 1 and 0. When you make it very small, I'm talking about 2007, they found that there is some problem or soft errors start to appear from the transistor. This is one thing. The second thing, when you have a lot of transistors on the same chip, the chip is heating too much, okay? So even the cooling system, like fans or anything, cannot cold this chip. Then it starts again to make soft errors and maybe even shut down the machine itself. Even this problem have been solved by some vendors. They can make the transistor smaller without any problems. But at that time, other people think in a different way. Okay, we have a problem, and it seems in 2007 that Moore's law will not exist anymore, even it survived after 20 years after that. But let's try to find another way. Then they talk about multi-core. Let's have multi-cores CPU on the same chip. So instead of having one, let's have multi of them and start to develop this pair processing. Okay, so multi-cores start to appear and adding more cores to the CPU. Even, as I said, other vendors still in the same direction of adding more transistor as Moore's law and still survive until now. Every year, from 2007 to now, you can find someone who will tell you that Moore's law will end this year, next year, the year after. And until now, this is not confirmed. During the days that we have now with the GPU, with other things, it starts to be a little bit not linear, but not yet ended. So today you can see some people say it's ended, some people not, okay? So this is about Moore's law and paired computing. But this is the only way you know. Also at that time, people start to talk about, okay, let's parallelize using distributed computing. Okay, the simplest case is the cluster. At KAUST here, we have something called IPEX cluster. It's a cluster at KAUST. Cluster is what? You have several machines, as I said, connected to each other using a network. Now you added, when you go to distributed system, you added another factor to the speed or to the power of your machine. Not just the CPU and the memory, as I said before. Now you also have a network, because this network will be used to communicate between different machines. So if this network is a slow network, even if you have a powerful processor, even if you have a big memory, this will not help, because the network will be a bottleneck. So when we talk about distributed system, supercomputer, cluster, we are talking about three factors: the computing power, the memory, and also the network that we have. So distributed system can be clusters or supercomputers. The main difference that on the cluster is machines that connected to each other in a network.
maybe the network is slow. Maybe the machines have different architectures, and you connect them to each other. When we talk about supercomputer, no, you need to tune everything. It's not a machine anymore. It's just racks of CPUs. I don't know if you visited already Shaheen 2 or not. Did you visit? They have some.
Impossible, unfortunately.
Sorry?
It was impossible.
Because of Shaheen 3. Oh, okay. Okay.
They didn't allow.
Okay, so you missed this. So if you go to Shaheen 2, the supercomputer is racks. I will show you some videos and picture now. But it's racks, all these racks containing the CPU and the memories, and are connected to each other using very high-speed network. Okay, so for example, Shaheen 3 has a network called Slangshot. Okay, Slangshot 10. The Slangshot 10 is a new technology in network, and it's very high speed compared to Slangshot 9 or even InfiniBand that's before the Slangshot technology. So this is important to keep. If everything tuned, you are talking about supercomputers. If it's just some machines you connect to each other, even with an Ethernet network or something, this is cluster. So why we need to do distributed computing? First, for, I don't know if this is working or not, scalability. Scalability meaning I'm solving now a problem. This problem size is X. I need to solve a 2X, 5X, 10X, 20X. So in this case, I need to scale. It's very easy to just connect CPUs. You will not need to do any development from the hardware architecture. Just collect more hardware and connect them to each other. Okay? Reliability, fault tolerance also because how many people here know about fault tolerance? Did you hear this term before?
Yes, error between the data and between.
Yes. So the fault tolerance is how much your application or your hardware are tolerant to any fault that happen. Physical fault, we call it soft errors or hard errors or hardware errors. Hardware errors are something happen, a node shut down, done. Software errors, that soft errors happening because maybe a magnetic field around the hardware or something that flip some bits here and there. So we call this fault tolerant. So those kind of system should be a fault tolerant system because you are running on different machines. If something happened to one machine, maybe you can use the other or the other node. Okay? Performance, I'm not sure. I need to come here a little bit, right? And performance because we need to run faster. However, the problem here that we have a complex architecture, complex construction of those kind of supercomputers and distributed system. I talked about the computing power, about the memory, about the network, but there is a lot of things behind. So let me give you an example. When we talk about Shaheen 2, I think, Shaheen 2, you need cables to connect the racks to each other, right? And those cables is very high-speed cables to do the network. Do you know how long is those cables on Shaheen 2? I mean by how long, meaning what? If I put all the cables on a straight line, how long this line will be? So imagine for Shaheen 2. It's too much, right? It's 20 kilometers. The cable, just the cable, okay, connected for each other. So this is one thing. The cooling system, what the cooling system you are using? We are using a water cooling system here, seawater. So you need tubes and you need the flow of the water and the temperature. So it's very complicated to design such supercomputers, okay? So we discussed about this. Okay, you are talking about performance, and we need supercomputers because of the performance. We need multi-core because of performance, but what's the measurement of performance? So how can I measure my performance? So this is actually, in computer science, everything is easy. It's kilo, mega, giga, terabyte, so we have the same terms here. But here we are talking about flops, floating point operation per second. So we are measure the performance of a computer or supercomputer by measuring how many floating point operation these computers can solve in 1 second. Floating point operation meaning, for example, 1.1 plus 1.1. This is one floating point operation. Okay? So we are measuring how many floating point operations this computer can solve, and this is the performance or the speed of this supercomputer. So kiloflops meaning that you have 1,000 floating point operations that can be solved in 1 second. Megaflops that you have 1 million floating point operation and you can go farther. Okay. The fastest supercomputer exists now worldwide reached to the point of exaflops. It can solve 10 to the power of 18 floating point operation per second. When we talk about performance, I'm talking again about two things. Okay, you remember we have a lot of 2 and 3. Two things. Theoretical performance and practical performance, or we call it the peak performance. Theoretical performance, that when the vendor sell you or give you the hardware, it will tell you that you can run on this chip, for example, 1 gigaflops per second. This is the theoretical. Because I have this number of transistors, I have this and that. But practically, you cannot develop a software that can run to this speed. So you can achieve 70% of the theoretical peak. This will be good. 80%, 90%, 95%. So you will lose some performance. And this is based on the hardware itself or the design of your software. Okay? So if you think about what I said from the beginning, you will find a lot of research area and a lot of developing on this area. So I can develop a software that can run on large supercomputers. Yes, this is a new thing, if no one did this before. I can develop a software that can get better performance than another software that's doing the same thing on large scale. Yes. I can develop a software that can achieve on a specific hardware more close to the theoretical peak rather than another software. So all of this is some kind of innovation on this field. So let's talk about what exists around us. The most powerful supercomputers today in the world, practically, is Frontier, an Oak Ridge National Lab. Oak Ridge National Lab is a national lab at the U.S. It's on the state of Tennessee. And this is the fastest supercomputer we have in the world now. The supercomputer has around 1,000,067 petaflops, which is 1.6 exaflops. So let's go back here. So as I said, this is the fast supercomputer reached to the point of exaflops. So theoretically, it has 1.67 EFLOPS. This is the theoretical peak. How many cores? It's 8.7 million cores. So think about it. Your laptop has 8 cores. So how many laptops we need to reach to this point? $1 million, right? 1 million laptop to put together, use all of them at the same time. This is what you can get from Frontier. Cost. Also, this is something, and this is why we can find supercomputer just in the kingdom here. Even, let me tell you that Qatar has no supercomputers. United Emirates has one, but it's actually related to a company. Okay, because it's very expensive to build a supercomputer. So this costs about $600 million. The second one, which again, I insist on saying practically, but actually the second one should be the first one. But it's not yet working on the full power. It's Aurora, and it has, or it can, has a theoretical peak of 1.06 EFLOPS, and it has around 4.7 million cores. Okay? I will need some of your observations about the numbers after the slides. So please focus on the number. So we have 8.7 million core hours with Frontier, and we have 4.7 million core, million core, not hour, million core on Frontier, and 4.7 million core on Aurora. The fourth supercomputer, so I missed the third one. Okay, I will tell you why. But the fourth is Fugaku supercomputer. This is in Japan, and the theoretical peak is about 0.5 exaflop, which is 537 petaflops, and it can achieve 442 petaflops per second. The cost of Fugaku is $1 billion. Okay? This is picture of Frontier and Fugaku, and maybe I will click here to show you. This is a link of course, the presentation also on Mark website. You can download it. So this is a virtual view of Riken Center of Computational Science, which has Fugaku. This is Fugaku. Okay, let me tell you one more time that you will miss visiting Shaheen 2. Okay, this is of course, but we cannot do anything. So even Shaheen 2, any supercomputers consist of racks. All those cabinets inside racks, as you see, the green lights, it's like the green lights you have in your network on your laptop or something. So this is the connection between the racks. Here you can go like you are walking inside Fugaku, and you see the cabinets, and maybe you see also the cooling stuff. Okay, so this is cabinet, and inside the cabinets we have racks. You can see the cables here. This is the cable connecting different nodes, and here you have a cooling system, air cooling system, and you have also a cooling, water cooling that go around the hardware itself to cool it a little bit. Okay, you can play with this as you want.
Shaheen 3, you're only using water cooling, right?
Yes, and even in Shaheen 2. So it's a little bit here. Okay, let me go back first. I am not sure if this will work or not. Yes. So the cooling systems depend on the environment itself. So here it's a little bit hot, okay? But still, the water itself coming from the sea can cool the system. So the water itself temperature compared to the temperature that we have around, water may be enough. And this is why we are using the water cooling system. Some supercomputer, let me go to the next slide, but I will still need to ask you some questions here. Something like in Finland, Lumi in Finland, this is number 5. So when the Europe countries start to think that we need to do one supercomputers together because it's very expensive, as I said, they decided to put it where? Why? That's it. So let's solve this problem by just putting it there. So it depends on the environment itself. You are deciding which cooling system you are using, because also this costs a lot of money. Okay? So you can go to top500.org. This is the rank of supercomputers based on their theoretical peak and theoretical performance and the peak performance, and you can check all the top 500 supercomputers worldwide. Let's talk about Asia, or what we have here. So we have Finland, Leonardo, Italy. We have Summit in US. The first supercomputer in, of course, in Asia, in China. Okay, and it has about 148 petaflops. Okay, so it's about 10% of the first supercomputer of Frontier, because Frontier can get 1 exaflop. This is 0.1. Okay, let's talk about Saudi Arabia. Recently, we have let's say 20% of Shaheen 3 running. 20% of Shaheen 3 running. Shaheen 3. Tomorrow I will do one slide. I didn't have time today to compare between Shaheen 1, Shaheen 2, Shaheen 3 for you to understand what's going on and why we need to pay a lot of money to have this supercomputer. But for Shaheen 3, we have just 20% of it, which is the CPU part. It's up and running, and we are number 20 now on the top 500 list, just 20%. Okay. Once we have the complete supercomputers, maybe in 2 or 3 months, hopefully we will go up again on the top 10 or even the top 15. Okay? So on Shaheen 3, for example, we have 35 petaflops as performance. And very fast number, Shaheen 2, the old one, it was 7 petaflops. Okay, so we are talking about 5x faster and just 20% of the system itself. And those are another system here on, we have also the MEM7 on Aramco. It was actually when it starts as number 17, then now it's number 31. Okay? I insist to go back to this slide. Give me some observation about what you can see here. The numbers.
I have a question.
Okay.
Why the fourth one is cost more and
This is good. You tell me.
I don't know, because it's in Japan.
What do you mean? Anyway, all those supercomputers, it's in Japan, but they are buying it from the US. Okay, from the companies like Intel, AMD, NVIDIA. So the cost is the same. We are not developing things in Saudi Arabia. We are buying things.
It's Japan, they are
Okay, Fugaku is, yeah, you are very correct. Fugaku is something else because the hardware on Fugaku is actually from Japan. Okay, you are very correct on this. But other supercomputers rather than Fugaku, they are using the same hardware. Okay, because Fujitsu Siemens is the hardware, the CPU there called Fujitsu Siemens, and I don't think that you heard about CPU called like that in the market, like Intel or AMD. But this is not the only reason.
Yesterday with David Keys, so we saw that computing was advancing faster than memory, which was advancing faster than bandwidth. And I believe Fugaku has a strong focus on bandwidth and memory, which might be related to its high cost. And also notice that it achieves more of its theoretical peak. Like with Frontier, its theoretical peak is almost 1.7, but on peak it's 1.2. Fugaku is almost 500, it's 450. Bit closer.
Yeah, but all those numbers, again, will give you one conclusion. The problem that when you buy hardware, it will be expensive and it will be cheaper by the time. So if you are developing supercomputers in the future and it has the same speed as another supercomputers from the history, it should be cheaper because just the hardware dropped price. That's it. Okay? Actually, I need to go faster. Maybe we can have offline discussion if you need on this. So what we are talking here about is to use HPC to do spatial statistics in large scale, to do spatial statistics computing in large scale. And this is one of the most used application on supercomputers today worldwide. About 60% of the supercomputers are relying on weather climate application to keep running. As Mark and Jan said yesterday, our problem that we need to solve a likelihood function, this likelihood function should allow us to get some set of parameters that we can use for the prediction, a statistical parameter. The equation itself has a covariance matrix to build using a specific covariance function, and this covariance matrix has a complexity in dimension equal to the number of locations. So with some small numbers, you can find that if you have 1 million locations, this means that you need to build a covariance matrix which is 1 million by 1 million, which is very big covariance matrix. And with some calculation related to the memory usage and the computing needed for solving the inverse, the Chomsky factorization of this matrix, you will find that if you have 1 million location, you need about 8 terabyte memory just to store it. 8 terabyte memory. Okay, think about this. Your laptop maybe have 128 gig or something. We are talking about 8 terabytes, which you cannot store in your machine. So you need, again, supercomputer that can store this. And to solve the likelihood problem, the complexity of computation is n cube. N cube is about 10 to the power of 18 flops. Okay, so 1 exaflop. So Frontier, the first supercomputer, which has 1 exaflops per second, can solve 1 million by 1 million covariance matrix in 1 second, theoretically, in 1 second. What if 10 million by 10 million? It should be theoretically 10 seconds. This is what the performance means. So how to solve this? There is 2 solutions. Okay, for a long time, the researcher took one direction, is to do approximation. I cannot solve this big 1 million by 1 million covariance matrix. So just try to approximate it somehow so I can solve it on my machine. I don't care about the accuracy, and that's it. The other direction which we took, and we took the both direction actually, is to try to use the HPC to solve the big problems very exact. And also when you enable the approximation, this means that you can go larger. So if I can solve on a supercomputer in this format 10 million by 10 million covariance matrix, if I approximate it, I can go to 100 million. Okay, so we reach to the point that no one reached it before. So this is the problem that we said, the complexity from the memory perspective is n square, and from the computation perspective is n cube. ExaGeoStat is the software that we developed here at KAUST starting 8 years ago, and now it's a mature software that can be used to solve or to solve problem on large scale on different supercomputers. The main problem behind ExaGeoStat is not the developing more than the design itself. Because at that time, we wanted to have linear algebra state-of-the-art linear algebra solvers for solving the inverse problem and other things. We need to have an HPC. We need to handle big data. We need to use the most recent statistical method that's used for the modeling and the prediction. So everything we need the best, the best, the best. This is one part. The other part, we need a software that can survive. Okay, so you can change in the future that run on a supercomputer. So when we call it ExaGeoStat, it's exascale geostatistics. Okay, Exa here for exascale. At that time, 8 years ago, there was no system that can reach to exaflops. But we developed our software that can run on the future systems that can go to exa and maybe farther. Okay, so this is the design complexity of the software. So ExaGeoStat is trying to take the advantage or the state of the art from each field to develop a very strong geospatial statistics software on large scale. The software currently supporting from the spatial stat perspective a lot of covariance function, including univariate, multivariate, space-time, Gaussian, non-Gaussian data, stationary, non-stationary data. So ExaGeoStat you can run on different data sets with different needs. We have three main components on ExaGeoStat. The first one is synthetic data set generator, and this one we used to test our software at the beginning. This was the idea. Okay, I need to model 1 million by 1 million data. I want to validate my code. I cannot use the real data set. I need to generate my own data set so that I can validate the code. This was the idea. However, when we build the generator, we use it later for the competition that Jan discussed yesterday. So we generated our own data set that no one did before, and we asked the other, use your approximation method to do the modeling on this. Okay? So this one, as I said at the beginning, was just a tool for us. Now it's a tool for the other also to generate very large data set to work on. Second is the main thing, which is the modeling, the maximum likelihood estimation. One function, we need to solve it several times to optimize a set of parameters that we will use for the prediction. And this function has a problem, a very big covariance matrix that we need to compute the log determinant for it and the inverse for it, which has a complexity of n cube computation and n square memory. This is the summary of the problem. Then the prediction, to use what we got from the modeling to do the prediction on the same time slot or even on the future. Okay? This three components, you can use it on climate weather application, you can use it on air pollution, you can use it on anything related to spatial field. So this is an example of how we are generating. I will not go on the math stuff. If you are caring about this, maybe you can look to the paper. Maybe you can ask a question offline. But we have some mathematical equation to do the data generation. The modeling, as I said, our main problem is this big covariance matrix that we need to compute the inverse and the log determinant. And this has this complexity, computation, and n cube on space. And this is also how we are predicting. If we have a set of location and a set of measurement, how to predict on the same time slot on the future. The design of the software itself, as I said, it's a little bit complicated, but we did this to do what I will discuss, something called separation of concerns. We need each component of the software to be a separate part, so that if we need to develop just on this part in the future, we can. Okay, let me give you an example. For example, there is a statistician who needs to develop a new covariance function in ExaGeoStat. Okay, he has a new covariance function that can model, for example, the Red Sea temperature very accurately. But this is not supported in ExaGeoStat. Can he add his function to ExaGeoStat? He doesn't know anything about HPC. He doesn't know anything about parallel processing. Yes, he can. Just writing one function, we can enable adding his covariance function to ExaGeoStat, and he will not care about anything. Just adding the function as sequential function as he is writing this on R, C, and MATLAB, and we can run it in ExaGeoStat. Okay, someone else have a very fast way to do the inverse for covariance matrix, faster than what we have in ExaGeoStat. He can go just to this part and develop his function, and he will not care about what's going on in spatial stat perspective or even on the parallel processing. So what I mean here that having a lot of layers on the software help us to extend the software, help the others to use the software, help the others to develop their own component or function inside the software. Okay? And this is why the software engineering is very important. You need to understand what's going on. For me, this was the board class in the bachelor degree in my software engineering. Okay, do this water flow design, do this, do that. But actually, when you go to practical things, yeah, it's very important. Very important to know exactly where you need to go, not just to write some codes and that's it. So the different layer of the software, we have first the application that we are climate weather application, the likelihood and the other on the modeling and the prediction, the inference. Then we need an optimization algorithm because we need to run this likelihood estimation several times to optimize the parameters. Then we have the linear algebra part. We need to do the inverse Chwalewski factorization for this matrix. So what kind of libraries we need to use. Then how we will do the parallelization. Then we have another big problem. Today, different supercomputers or parallel computing environment has different architecture, and they need different way for coding. So if you have you need to develop something multi-core for your machine, you are using OpenMP. If you need to go to supercomputers, you need to use MPI. No, but I need to enable the GPU, so you need to use CUDA. So each hardware architecture has different way. There is no standard here. And this is why we relied on something called dynamic runtime system. This is a very complicated layer that used to facilitate running your code on different hardware architecture without any problem. So you just develop on top of the runtime system, and the runtime system will run this on different hardware architecture. I will not go in details on this. But actually, this point allow us to run on different supercomputers that we have today. So for example, ExaGeoStat already, we run it on Frontier, on Fugaku. I need to change the number here. As I said, Fugaku is number 5. Summit, Hawk in Germany, Shaheen 2. We have some run on Shaheen 3. We are now trying to run on Aurora. So we run ExaGeoStat everywhere because of with the help of the runtime system. Regardless of the architecture of this supercomputer, we don't have a problem to run the software there. So this is the concept of a separation of concern. We try to have different parts of the software so that we can develop on a specific part without touching the other part in the future. You can make advanced numeric algorithm, do a new Chwalewski factorization, like what I said, the Taylor rank, David discussed this yesterday, mixed precision. I need just to go to this part. I don't need to touch the others. I have new covariance function. I need to have non-Gaussian modeling. I need to have a new thing, so just touch this. I need to run on a new hardware architecture that's not supported on this runtime system, so I need to develop on this. Okay? So this is about dynamic runtime system. As I said, it's a complicated layer. It's used to do some kind of API for different architecture that we have today, rather than develop a separate code for each architecture. On runtime system, the main idea is you are giving it a sequential code, like what you are doing on your laptop, but divide it to tasks, to small tasks, define dependencies. For example, I need A is equal to 1, B is equal to 2. Then I need to compute C is equal to A plus B. This is a very simple example. Let's parallelize it. Can we run the 3 statements at the same time? I cannot. I need first to run the 2 statements in parallel, A is equal 1, B equal 2. Then the last statement needs the input from the first statement to do that. Okay? So we draw this. I don't know if we have, no, we don't have a board here. So we draw this like this. Sorry? Yeah, just let me very fast. Let me use this. So this is the first one, A equal to 1. Can you see? I assume yes. So we call this a DAG diagram. That's it. I draw this, so I know that I can solve this on time 0, and solve this on T1. I give this to the dynamic runtime system, and he will know when to schedule the task and when to send the task to a different processing unit and how. There is some example of existing runtime system like Quark, Parsec, StarPu, and in ExaGeoStat we are supporting 2 runtime systems, Parsec and StarPu. Okay? So let's talk about the linear algebra part. So we're done with the first one, which is the runtime system. Let's talk about the linear algebra part. We need to do what? We need to do Chwalewski factorization or solve the inverse of this big covariance matrix. So the best way is to do the parallelization is to divide our matrix to tiles. So we have a big matrix. Let's divide it to small submatrices. Send, in the simplest way, send each submatrix to a given processing unit to do it. That's it. So, again, I'm talking about the simplest case. For here, if I have 16 CPU, I can give each CPU 1 tile to work on it, done, at the same time. It's not that simple because, of course, we have this kind of dependencies and maybe we cannot run at the same time everything, and this is the complexity of doing parallel processing. But this is the main idea in general. So, in the tile-based algorithm, this can be parallelized. You can run it on a dense way, and that's it. And we did this on ExaGeoStat in 2017, the first release of ExaGeoStat. Then after that, we start to support ExaGeoStat with different approximation method. Let's go with the approximation now, but on large scale. And we start to develop different design of our covariance matrix to help to speed up the operation. So first thing, we develop this version, which we call tile rank approximation. I think David mentioned this yesterday. The tile rank approximation meaning that each tile that we have, we are trying to approximate it to 2 matrices, U and V. So let me go here. Using SVD. So we are using the SVD approximation to compress each tile, not on the diagonal, and I will say why. Okay, I'm sure that you cannot remember this. Mark yesterday the 3rd or the 4th slide. He mentioned some important feature of spatial statistics related to the distance.
It is azimuth mode, so you take to that direction.
Yeah, okay, this is a feature, but not the one that I'm talking about.
Is it points closer together are usually like similar value, but
Exactly, this is the one. So about the distance, if you have very close location, most probably that they are related to each other more than very far one. So this is why usually when we try to approximate an ExaGeoStat, we are keeping the diagonal dense as it is. Okay, to keep the matrix positive definite, this is one thing. Second thing, because this diagonal means the correlation between the location and itself. Okay, and this is, should be a very strong correlation, so we are not approximating this. So the diagonal we keep it as it is, and then for each tile we are trying to compress it. Compress it meaning what? You are reducing the memory, so good. If the dense supercomputer, the dense covariance matrix can fit on 100 node of Shaheen 2, when you do this compression, you reduce the size, so I can fit it on 60, for example, yes. So you can reduce the memory, this is one thing. Second thing, the operation itself is faster compared to the dense one. However, you should take care, of course, when you are doing approximation that this is not impacting the results that you are looking for at the end. And this is what we did in ExaGeoStat. We have this tile low rank approximation. It's faster, need less memory, but at the same time, it's preserve the application accuracy at the end. Okay? So this is an example of TLR. I will not go in detail here. Then recently, 3 or 4 years ago, we jumped to mixed precision approximation. So all of you know that when we code something, we are defining thing in double, and float, and integer, right? And we start to work on it. What's the difference between double, for example, and integer? The size, exactly. So the double represented on the memory by 64 bit. The integer is represented by 32 bit, so half. So if I am representing my covariance matrix as a double, and I will need 1 terabyte, with very simple calculation, if I represent it in integer, I will need half terabyte memory, right? Just 64 to 32. However, when you do that and start to do your calculation, you cannot keep the accuracy that the application looks for. So we tried first, okay, let's not define the covariance matrix as double. Let's make it integer. We can reduce the memory, and also this will be 2x faster. But this will impact the accuracy. So this is why we design or develop what we call mixed precision approach. Mixed precision approach, let me go back to this. It's something, let's go to this one. Here. We will represent each tile with a different precision. Okay? We have our theoretical way to define which tile to use with which precision. But in this way, we can still run faster, maybe not faster as single precision, totally single precision, but still faster, and preserve the accuracy. And this is something from our recent work, and this is what even David mentioned yesterday about the Gordon Bell Prize finalist on 2022. It's related to this. Just to have different precision on the matrix, giving the accuracy we are looking for, and speed up the operation. But why we look for mixed precision? You are talking about speed up of 2x if we make it single. But if we have mixed precision, it will not go to 2x. It will go to 1.3x or something. Why we need to develop something that will not give us this fast execution as expected, 5x, 10x, or even 100x? Because recently, the NVIDIA GPUs start to develop some hardware that helps to run lower precision faster than double precision by a magnitude reached to more than 20 and 100x. And this is why we developed ExaGeoStat recently to run on a GPU with this mixed precision technique to take advantage of this. Let me give you some numbers. I'm sorry, Mark, we need to finish 9:30 or 9:45? 45, okay. So these are the three recent GPU architecture from NVIDIA. V100, A100, H100. For V100, the performance, now I think you are smart enough, peak performance, you know about this, right? One GPU, this is the highest performance that I can get from this one, not the theoretical. Okay, this is the peak. So the peak performance of V100 is about 7 teraflops. Let me tell you, for a CPU like Intel CPU, you can reach today to 2 teraflops, for example. Okay, so 7 already is something big compared to the CPU. Then on V100, they have for 32, 15.7. It makes sense. Double precision, you will convert it to single precision, so the speed up is 2x, so from 7.8 to 15.7. Then they developed something called Tensor Core at that time. This Tensor Core is hardware inside the GPU that can help you to run FP16. 16, we call it half precision, so it's half of the single. Very fast, with the performance reached to 125 teraflops. You look, we are talking about 9x speed up, just if you can represent your data on half precision. Then after that, the A100 came. Of course, we have boost on the performance of double precision run, but also they developed Tensor Core for 64 and for 32. The speed up here is 2x. The speed up here is 1 point something. But here with 16, it reached to 624. Now with H100, this is the new one, that we will have the Grace Hopper version of it on Shaheen 3, has those numbers. So if you can enable lower precision, this is the conclusion. If you can enable lower precision in your application, you can take advantage of the performance of the Tensor Core technology. This is it. This is the message that we received 3 or 4 years ago and start to develop the mixed precision ExaGeoStat because of that. This graph shows some speed up between if you develop something on different, actually this is B100, the version before V100, H100 is not here, just to do one Chomsky factorization on one GPU, how fast you will go if you do it on lower precision. And you can see that we can reach to 10x speed up between what? Between enabling totally half precision, 16-bit Cholesky factorization, and this one, which is double precision. So double precision covariance matrix and half precision covariance matrix solve the same problem. We can get 10x speed up. But again, the problem is not just to reduce the precision and push your work, because maybe when you reduce the precision, the accuracy of the application is not good, so you need a trade-off. I will show some results here related to what we did for the 8 years, just to give you impression about the application and what we are doing. This is, for example, our I think this is our second paper related to use tile-Lorenz for our operation. And on this paper, we solved two problems. Problem related to a 2 million location soil moisture data set at the Mississippi area in the US, and 1 million location of wind speed problem in the kingdom. I think it was, no, in the Middle East. Okay? So we solve it using ExaGeoStat, using tile-Lorenz approximation at that time. As I said, we have a lot of support on different covariance functions. This is an example of multivariate modeling using exact and tile-Lorenz. Also on trivariate data set of U and V component of wind speed and temperature. So now we are doing the modeling not just related to one variable. We can combine a lot of variables and do the modeling. For example, of course, you know that the temperature and humidity somehow are related to each other, So maybe if you model both of them together, it will help you to get better modeling. So this is what we call multivariate. This is non-Gaussian support. So sometimes your data set is not that Gaussian, and you need to have some features to capture the non-Gaussianality on the data. And this is one paper about the non-Gaussian modeling on, I think this is also wind speed, but just on the Arabian Sea here in the Middle East. And I think we have another map here related to precipitation on Germany. Okay, I think it was 116K or something, precipitation, and to model the precipitation in Germany. Spatiotemporal, so all what we are talking about space. So one time slot, let's model. Can we model the future? Can we see what's going on? Yes, and we have one paper on this, and this is show the air pollution. This is an air pollution data set on different time slots, and we are trying to model what's going on to predict in the future. This is the data set that we used for our Gordon Bell paper related to ET data. Okay, I cannot pronounce the full name. Okay, but this term related to the water under the land, and because we were using, and this is one thing very important. At that time, Fugaku was number one, Fugaku at Japan, and we need to ask them to run there. So we said that we will have a data set from your region, from Asia. So we took, as I remember, the map was from Afghanistan, something like that. So we told them, okay, this is the data set that we are working on. Then they gave us an access to run there. So you need to mention to them that you are doing something important for them, because they paid money for that. This is why we used this data set at that time, because of Fugaku. And this is some results related to accuracy. Of course, if you are somehow interested on what we are doing, you can go to the paper, you can ask us offline, Mark and myself, you can get our emails very easily. So this is the development timeline, and this software took 8 years, okay, from us, okay, so it's not something easy. And it's very important to highlight to you that even you can see that I just put statements that we used a lot of time and efforts to do that. So we started in 2017 just to do a parallel version of dense ExaGeoStat, and we released the software version 0.10. Then the second year, we have this tile-Lorenz support to do low-rank approximation and make things faster and running on larger data sets and supercomputers. In 2019, we have this mixed precision idea. Tensor core is there. Tensor core is there, and we need to take advantage of this. Then we did mixed precision idea. Then we have 2020. I call it, you can see that I named every year, but this year I call it COVID-19. That's it. We cannot call anything related to science here. So in COVID-19 year, we start to change our mind to actually collaborate with the University of Tennessee team there to support ExaGeoStat with Parsec because it's more powerful runtime system compared to StarPU, and we have released our new ExaGeoStat. 2021, we start to have new heights. We think, okay, now we are developing to do approximation, but we are not supporting different covariance functions that statistician needs. So we start to have multivariate space-time support and even doing parallel optimization. Then in 2021 also we have the idea of doing the first CAST spatial stat competition. Let's generate data set and involve the others to do approximation. And it was a very good competition that pushed us to do the second and the third in 2022 and 2023. Then this last year and this year we are focusing to move our data, our application is a C-based application. We move it to C++ this year to make, we re-engineering the software at the beginning to allow the other to contribute and also to have better performance and better look to the software. This is our software that we have online, ExaGeoStat software, the main software. We have the R version, but recently we also released ExaGeoStat C++, which support running in R and C. We will run some examples with Jan tomorrow, practical example using ExaGeoStat to show you what's the advantage of the performance, what's the advantage that we have, what's the parameter to play with, how to do some examples in R. So we will do this tomorrow with Jan. I think that's it. Yeah, this is it for today. So first we have, I think, 5 minutes. If you have any questions or comments.
I mentioned before that you use the MLA estimation method to estimate the parameter, right?
Mm-hmm.
So can any estimation method other use or just MLA?
With ExaGeoStat, we are developing the MLE method, okay? But you still, if you need, as we discussed with Mark yesterday, if you need to use a machine learning method, I cannot remember who mentioned k-nearest neighbor, for example. All these methods you can use to predict or get something, but it will not be that accurate compared to MLE. Okay, so you still, you can take the average of the cities around you and that's it. But machine learning may work fine with you, but we have a problem with machine learning that I can describe to you using MLE what's going on. Machine learning cannot describe. What I mean here that I will tell you that there is a correlation between the location and this is why we get this parameter that high, so I can explain. Machine learning will just predict you and cannot explain. This is a problem, okay? So you can still use anything, but inside ExaGeoStat, just MLE for now.
Talking about the peak and the vertical performance, what factors really impose these limitations in the performance?
Okay, let me tell you the truth. The truth. So the theoretical is coming from the vendor, as I said, just calculation to tell you. The peak performance coming from one software. Okay, this software again developed by University of Tennessee, and because those guys, Jack Dongar, there is the guy who are leading HPC. You need, when you do a supercomputer, to take this software and run it on supercomputers, and the number that you can get, this is the peak performance. The software called LIMPAC. Okay, and actually it's matrix vector multiplication. So you just, what you are doing, once we finish Shaheen 3, we took the software, run it on Shaheen 3, and the numbers, the performance number we got to solve this matrix vector multiplication is our peak performance. But still, in general, the definition of peak performance is the highest performance you can get in any software on this hardware. Any other questions? We still have 4 minutes. Go ahead.
Why we can't make one big supercomputer?
Together, yeah? This is the same idea of why not make one big army, for example, together. So you have your own, I mean, yeah, it's a political thing. Actually, supercomputer is very, very political. Okay? So, for example, the boost you can see on the supercomputers in the US, once Japan have this Fugaku in 2021 as number one, Donald Trump pushed a lot of money to the national labs to develop supercomputers to be the first, and now they have actually Aurora and Frontier. So the money that Donald Trump pushed, they put them on the front. So it's a political thing, okay? Yeah, we can do everything. We can be very nice.
I mean, why it should be distributed? Why we cannot make one, just one?
Oh, okay. One meaning what? One CPU, big CPU that... I don't know. I think physically we cannot design something like that. But think about it. Is it better to do something, and if there's a problem happen to this chip, for example, that's it? Yeah. Or it's better to try to have different power. So even though supercomputers survive for 5 or 6 years, sometimes they are changing some hardware there. But yeah, maybe you can do it.
I have a question in regard to ExaGeoStat. Yes, it solved the big data problem on big data sets. But looking at to it today, is there any limitations that we are really thinking of in the future to solve in regard to this?
Limitation.
Solve something, but is there still some limitations or not?
Let's talk about challenges, not limitation. This is better? Yeah, the challenge is that today there is a lot of developing on the hardware sector, the companies. They are developing new architectures. And we need to taking advantage and develop an ExaGeoStat based on that. For example, the Grace Hopper chip that will be on Chain 3, until now we don't have an optimized version to run there on ExaGeoStat, and we are trying to do so. Okay, this is one challenge from the hardware perspective. The second challenge related to science itself. We need to support more operation on the software so that we can make the others use other software instead of existing software. And this is not easy, because if you develop functionality with a small software, just in R or MATLAB, this is fast. But to develop it in parallel computing, it's hard. So to support a lot of functionality, this takes time. So this is challenges that we are trying to keep everything up to date, and also allow the others to contribute to our software, maybe to develop from their side. Okay, thank you so much for today. And see you tomorrow.
In particular, why we have no many different supercomputers. In our computations, we need a lot of shared memory. But when we began this work, it was the beginning of chaos. I visited some center in United States which produce supercomputers, and they said, we have one experimental supercomputer in our center. You can use it, but we do not produce these things. So it's better to have supercomputers, clusters. It's better to have very serious servers. We have such one. So it's better to have, different things. If you are concentrated only on one, it can be dangerous. It's general idea.
This is one thing I didn't mention about the MAM7 in Aramco, for example. They are using it for doing a lot of simulation related to the oil and gas industry. So actually it starts to use somehow supercomputers in industry, and it helps a lot for doing a lot of simulation that save some money. Okay, so instead of doing things practically and you are wasting your money here and there, you can use simulation and supercomputer and know exactly what to do on the real time. Okay?
So thank you very much.
Thank you.
Tomorrow we'll have last lecture.
Yeah, we will have some practical example. I will join Jan tomorrow for 1 hour, maybe to give more insights about the software. Thank you.